Hello everyone. Today we are going to see the topic minimum spanning tree using kruskals algorithm. First of all, what is tree and what is graph? A tree is a collection of nodes and graph is a collection of vertices. And the main difference can also be a graph can form cycles and tree cannot form a cycle. Now, minimum spanning tree, which is also known as minimum cost spanning tree, defined as a spanning tree that has a minimum weight among all the possible spanning trees, or a subgraph of a graph G of v comma e without having any closed region, loop or cycle. Properties of minimum spanning tree. There are totally three types of properties, in which the first property states that the cycle must not be formed, that is, no edge should be traversed twice. Now, the second property states that a spanning tree must include all the vertices of a graph. And finally, the final property will be if a graph has n vertices, its spanning tree will be consisting of n minus 1 edges. Now, let's take a basic example for converting a graph into MST. Consider a graph ABC with a cost 3, 4, 2 respectively. Now consider the property. From that there are totally three possibilities. A connects to B and C, C connects to A and B, and finally B connects to A and C. Now check the properties. No cycle is formed in any of the three cycles. It means first property is satisfied. Second, all the vertices of a graph ABC is included. Second property is also satisfied. Finally, the third property, initial graph has three edges, but the MST converted three possibility graph as two edges respectively. Final property, if n vertices are there, then there will be n minus 1 edges is also satisfied. There are two types of algorithms to find the minimum cost spanning tree: kruskals algorithms and Prim's algorithm. First, we will discuss about kruskals algorithm. Kruskals minimum spanning tree. Kruskals minimum spanning tree algorithm is to connect all the vertices of a graph with the minimum total edge weight while avoiding cycles. This algorithm employs a greedy approach, meaning it makes locally optimal choices at each step to achieve a globally optimal solution. Algorithm. First, it sorts out all the edges of a graph by their weights, then starts the iteration of finding the spanning tree. At each iteration, the algorithm adds the next lowest weight edge one by one, such that the edges picked until now does not form a cycle. Simply list all the edges in order based on their cost from lowest to highest. Select the edge with the minimum cost from the edge list and add it to the minimum spanning tree if it doesn't form a cycle. If it does form a cycle, discard that edge. Repeat step 2 until all the vertices are included. Let's take an example. The first step is to arrange all of them in ascending order. This is the edge list. Add the vertices to the spanning tree one by one. Let's select the vertices A and B since it has the minimum cost edge 2. Then DE as the next minimum cost edge 2, so adding DE to the edge graph. Again step 2 until all the vertices are covered. Now consider AC as a value 3. Ensure that no cycle is formed. Now consider BD, which has a minimum cost of 3. Now connect BD and check or ensure that any cycle is forming or not. No cycle is formed, right? Now the next step is to follow the rule 3 until all the vertices are covered. Now adding the next edge DF and still no cycle is formed. Since all the vertices are obtained, we can stop here. Even if we try to add BE, it forms a loop. CE, it forms a full cycle, so we won't consider. Then add BC, it forms a short cycle. Now even if we add EF, it forms a cycle. We can stop here. Since all the vertices are covered, this is the original spanning tree. We will find the cost for the obtained MST. Add all, we will be getting 13. Now consider the original graph and obtained graph. There must be n vertices in the obtained graph. That is 6 are there. Then edges will be n minus 1, which must have 5 edges, hereby ensuring that now cycle is not also formed. This is the final minimum spanning tree using Kruskals algorithm. Thank you.